There's a place in our universe, a marble spinning in a vacuum. It contains life. It contains us. It may look solid and enduring, but now we can see it differently, across time, living and breathing. Across time, we can see that we, all of us, are changing this place faster than ever before. We can see the impact of the way we live. Of the choices we make. And see their consequences. There's a place in our universe. How we decide to treat it today will determine our future. What will you think? What will you do when you see our world changing before your own eyes?
This guy named Bob Bunting is going to get us started. Bob's going to talk about the forecast for the Sarasota area, for Florida in general, and then use that as a microcosm for what's going to happen in the world. Bob?
Well, good morning, everybody. And wow, it's finally happening. It seems like a long time in planning. And as you can imagine, live TV never turns out exactly the way you want it to be, but we'll do our best. First, I want to thank everyone for coming. We have an amazing audience today. It's self-selected. There were a few people we invited, but not too many. But it's amazing. We have 50 people here from private industry. We have 50 people here from government, and we have 50 people here from academe. And that, I couldn't have designed it any better if I tried. And all of you self-selected to be here, to come and to be part of this conference. Some I see have been here before for the first conference, but I see many new faces. And so I just wanted to welcome all of you here today. I hope this will be, it's going to be sobering, I'm just going to tell you. But I am an optimist, and I believe that human beings were put on this earth, that we're different from any other species because we have free choice. And if we use it, we're going to have a decent future ahead of us. And if we don't, we are going to pay a terrible price. And it will be a choice, and the CAC is here really to help inform that choice so we make better decisions to start acting now, because climate is one of those funny things. You may not think it has changed much now, but I hope when you watch that video you realize how much it has changed. But the rate of change is increasing, and what's in the atmosphere right now is going to continue to change the climate for 200 years if we don't put another drop of carbon in the atmosphere. So it's in the system. We're going to have climate change and more of it. and we're going to have things like sea level rise, increasing hurricanes, et cetera, which we're all going to talk about today. And it's baked into the cake at this point. So we have a future where we can decide whether we want to get to net zero or not, and we had better. But if we don't, if we were there today, we're still going to face quite a few challenges in the upcoming decades. So this is the forecast for 2030, 2040, and 2050. We're not going to get bogged down what's going to happen in 2100 or 2200 because everybody else is talking about that. But our communities that we live in are going to have to really jumpstart the reaction and the adaptation and the mitigation of the worst impacts of climate warming right now. Because if we wait to 2030, it's going to cost a lot more money to adapt. I'm not really sure people get this yet, but I hope when we leave this conference today, people will understand that's where we are. So with that, we'll get started. So this is the forecast, as I said, for 2030, 2040, and 2050. We're going to start with two things. What has happened? Where are we right now? You can't forecast the future unless you know where you are. Somebody didn't get their video link and are calling me. Bob Carell, I cannot talk to you now. Look on your Zoom. So anyway, I hope everything's okay. Bob will be with us in a bit. So the quote that's often said is, if you do the same thing over and over again and expect different results, that's the definition of crazy. And I want to tell you that was not Albert Einstein who said that. I don't know who it was, but they were really smart when they said that. And for 50 years, we've been working on a top-down approach to hoping government was going to save us from climate warming. It's been an abject failure. I just want to say, we have spent a lot of money, but we have increased what we know. We now really know what we're talking about. But what have we done with that information, and why haven't we used it more? And the problem is not science, it's people. And the whole problem that we have really is people. It's not science. The science is great now. We've gone from alchemy to chemistry in weather forecasting and in climate forecasting. But we haven't figured out how to get this information into our heads in a way that we get it, so that we're willing to move forward with solutions. And we have to do that now. So here's the 800,000 years of data. 800,000 years, and what I want to show you is that on the left-hand side is 800,000 years, and that's carbon on the right-hand side, how much carbon dioxide we have in the air. And carbon dioxide, of course, is a greenhouse gas, as we all know. And then you'll see that dotted line where the carbon increased to a certain point and then went back down. Those, my friends, are the warming in the ice ages. And now look on the right-hand side. There's a singular dot there that's never happened before in 800,000 years of where the carbon is now. It's not a theory that CO2 is a greenhouse gas. It's not a hoax. It's a fact. And that fact right there, what it says is, oh my God, there have been times before where carbon was way lower than this. And 100,000 years ago, for example, there were 20 feet of water right here where we're standing. And now we have way more carbon in the air. And when you hear about carbon sequestration, the reason it's so important is we got to get that carbon down, and we got to do it fast. Because the atmosphere is a buffer. It takes in that carbon but there's a lag time before you turn on the heat on the fire, and you can put your hand on the stove for a long time before you feel the heat. But once that heat comes on, you can't turn it off. So that's pretty much what's going on. Here's another look at it. These are the greenhouse gases we provide to the atmosphere, and you can see the slope since the beginning of the Industrial Revolution around the late 1700s. And there's no question that the cycle changed as soon as humankind reached 1 billion people and started industrializing. The greenhouse is, thank God we have a greenhouse effect, because we wouldn't be here otherwise. So our greenhouse gases, water, is only 0.4% of the atmosphere, 0.4%. And it creates havoc across the world. And it also is necessary to grow all the food we eat. And so even though it's a trace gas, it's very, very powerful. But CO2, let's say that's a factor of 1. The next one down is methane. And methane is 50 times as powerful as CO2. And nitrous oxide is 300 times more powerful. And these are gases that we're putting into the atmosphere a lot more because of humankind. So the trace gases are increasing fast, and so is our temperature. Here's another view of it. This time I broke out sea level rise on the bottom, CO2 on the top, and you can see we're in uncharted territories, and the global temperature average. And you can see that while CO2 is at a record every year, the temperature is just now breaking out of a trend and going to a place it has never been before in a long, long time. And sea level rise is responding to that. We came out of that ice age, and now we're losing ice very fast. It's just a direct response to melting. I mean, it's like putting ice cubes in your glass, putting it on a 90-degree counter outside, and you go outside to sit down and your ice is gone, and you say, what happened? How come it melted so fast? Well, it's 90 degrees. It's not rocket science. So when we look at emissions, we can look at all the different sectors, but it's incredible. Industry puts in 21%, transportation 24%, and a lot of people will be surprised. Look at agriculture. Did you really think growing food put that much carbon in the atmosphere? You thought it was cars. It isn't. I mean, it is, but it isn't. Here's what it looks like from looking at it slightly different. You can see energy, making energy for electricity for any use is 73% of the carbon footprint, and agriculture there is the second biggest. Then let's look at where it's coming from. This is a sobering graph here, because China really is up to 30% now of all the emissions in the world, and the US is down to less than 15. So all the 5 largest contributors under China are less than China. So when we talk about cutting carbon, we have to have China help, because if they don't, we can't lift that much by ourselves. So this is a sobering thing. If they don't want to, our goose is cooked, so to speak. This is another view of it. On the left side is Asia, and on the right side is the rest of the world. And you can see that with the growth in Asia's economies, we have a lot of pollution and emissions coming from there. The United States is getting more and more efficient. We've already cut our carbon footprint since 2005 by 20%. And it's because American industry is getting the job done with new products and services. We're not doing it quick enough, but we are in a trend down in this country. China is still moving up quite dramatically every year. If we look at, for instance, electric power generation, in China you can see 238 coal power plants are planned or being built. The United States isn't even on this because we don't make any anymore. But when you hear from the Paris Climate Accord that we're going to start reducing coal, it's China and India that can't really do it because they could never supply the energy that they need right now. If they did, they have no other choices. So it's an opportunity, in my opinion, for the West to sell products and services to the Chinese that can get this done. And for people who are afraid of nuclear energy, I would say, would you rather drown? That's pretty much the choice we have. I mean, I don't really care to have nuclear energy myself. I wish there was other ways, and there will be, but nuclear energy is an option, and we need to use it, and we need to use it big time now. So the past climate tells have been about ice cores, sediments, rocks, etc., measuring the past. And all of these things on this chart we can measure in sediments and ice cores. And this is in Colorado. I promised Elizabeth we were going here. This is where we store all the ice cores from 800,000 years in a big, it's giant, very cold, and in every canister are ice cores, and every single one of those has a pollen, CO2, how much, every other trace gas, even debris of what the past climates were, and we can study those. And this is what one of them looks like when it's out of the sheath. So when you go in there, it could be 100 degrees outside, but it's cold in there. So over the past 10,000 years, we've gathered all of these various data from the last 8,000 now, and you can see on the right-hand side again, by direct air measurements, we're measuring the increase of carbon dioxide. So let's see how this is done. Go ahead and, let's see, I'm supposed to click this twice, am I not? Or thank you, Kurt.
Melting about 2,500 years worth of ice from West Antarctica. This is part of a big national project aimed at uncovering climate history and glaciology in this region. Ice cores are a really great way to look at climate history. They're not the only way, and for certain locations on the Earth, you can't use ice cores. But at the poles in Greenland and on the Antarctic ice sheet, ice cores are a great high-resolution record that allow us to look at hemispheric and global scale climate change. There are plenty of other really good ways to look at climate history. For example, corals, tree rings, lake sediment cores, ocean sediment cores, and every different type of record allows you to address a question in a different way or in a different location.
We are melting an Antarctic ice core for the Waste Divide project.
Like I said, live TV.
I'm working on melting about 2,500 years worth of ice from West Antarctica. This is part of a big national project aimed at uncovering climate history and glaciology in this region. Ice cores are a really great way to look at climate history. They're not the only way, and for certain locations on the Earth, you can't use ice cores. But at the poles in Greenland and on the Antarctic ice sheet, ice cores are a great high-resolution record that allow us to look at hemispheric and global scale climate change. There are plenty of other really good ways to look at climate history. For example, corals, tree rings, lake sediment cores, ocean sediment cores, and every different type of record allows you to address a question in a different way or in a different location.
We are melting an Antarctic ice core for the Waste Divide project. And here we have the melter system. We come in here every day, 10 hours a day, and melt as much ice as possible.
And it's a way to look at the interactions of the atmosphere, the ocean, and the Earth's surface itself. We're measuring the water flowing by continuously. So we get a dust record and a conductivity record. And both of those things have an annual variation in them. And so in those wiggly lines, we can see an annual signal, kind of like tree rings. And we can't really see that in this ice. But as we look at the chemistry that comes out of the ice, we can see that annual record. Okay. I'm going to turn up the pump. So we have a clean lab where we melt the ice core. The ice is melted from one end to the other on a hot plate. You can hear the sound of the core. It's pretty neat as the ice melts. And the water is pulled through that plate, allowing us to get the inside of the ice core without ever having the outer part contaminate that inner part of the core. For the ice that we're melting today, a single year is about this much ice. And so if you imagine the stuff we're measuring on a really high resolution, through that year we can see changes happening and actually figure out what season these changes are happening. You can reconstruct the temperature of Earth, or the local regional temperature, so Antarctic temperature. You can reconstruct the strength of the winds, or the strength of the atmospheric circulation around Antarctica. We also see volcanic eruptions, and actually today we'll be melting ice that may show evidence of an ancient volcanic eruption, which would be very exciting. So these are top up arrows. So the top of the core is here, and we melt top to bottom. And that way we can connect all the segments of ice, because they're in 1 meter segments, and create a long record. Minus 20 C. Not that much colder than a typical winter day in Maine, but still cold enough to suit up. I'm prepping the cores to melt. So I need to clean the ends of the cores. There might be some dust or particles that have just sort of stuck on the ends. So I scrape those off and get the ice into its core tray. These are ceramic blades, so they should not contaminate the chemistry of the core, and we clean them every day. Everything in the ice core world is very sensitive, because these are pristine records of ancient atmospheric chemistry, and we have to treat them that way.
I mean, I'm helping Bess track volcanic eruptions in an Antarctic ice core that spans back to 2,300 years. I mean, where else am I going to get an experience like that?
2.5 centimeters a minute. So we actually had a really interesting conversation out in West Antarctica. The fact that we're taking about 2.
There we go. Okay. So I think you know now that this, how people know about what happened before, we really know. Now I want you to take a look at, I guess, father time or mother time, or however you want to put it. But there's the 24-hour clock over there. And I don't know if you can see, but it says humans on the 24-hour clock showed up at 11:58 p.m. and 45 seconds. The Earth is 4 billion years old, and we've been around for 20,000 years. It's not necessary that we're here. We are not that special, except for what I already told you, that we have the power to decide what we want our fate to be, if we want to decide. And not making a decision in this case is one. Let's see here. I can't get this to move forward now. There we go. So methane. You may have heard a little bit about methane recently. Whoops. Oh, don't steal my thunder, so to speak. Methane is 50 times the impact of CO2. This is an infrared camera flying over what looks like an inert desert, and we can see where the methane's coming from. So we know where it is, and we know how much of it there is. We can't see it in our everyday life, but with our technology now, we can see it all. And of course, here's the culprit, right? We've all heard about cows and cattle. And of course, yeah, there is CH4. There's no question about it. So the problem for these poor creatures is not so much that they produce a lot of methane, which, you know, they do, but where they're in feedlots. This isn't how it used to be. They used to roam around on the planet in the savanna and the prairies, and they weren't cooped up. And when they were roaming, they were able to pee and poop all over the place and grind it into the soil, and that would attract microbial activity. And pretty soon, the plains that weren't so great became the Great Plains. And that Great Plain is feeding the world now. And it's because we had animals that were roaming free. So in the system, they're not bad. In the system, they're not necessarily bad. But the way we have decided to raise them for commercial purposes is bad. So one of the biggest payoffs we have right now is lowering methane because it's 50 times more powerful and it's a trace gas, and we can do something about that, and we can do something about that pretty quick. Also, I just wanted to say, it's not just the cows, okay? Termites produce 10% of all the methane, and it's natural. They eat cellulose, they have anaerobic bacteria in their guts, and the output, so to speak, is methane. And I just wanted to say, none of us are immune. So this is brunch on the bay. And, you know, the bull, he's right in the backyard here. You'll see him at lunchtime. But I was taking a picture back there, and he said, "Was that you, Bob?" And I said, "Don't blame me. You're the problem." Anyway, so we've had this double whammy. 36% of all the crop land that we have feeds livestock. 36%. That's an incredible amount. There are 915 million acres of land in this country that grows food. 915 million. 36% of that is to grow animals. So we've had basically this process of turning forest into less productive carbon sinks, let's put it that way. And these feedlots and the way we grow food are directly responsible. In a natural system, we could grow food without this impact, but it's not as profitable. So it's just not the beef, it's how we raise it. Another story is Teddy Roosevelt, who was our conservation president, and he was a big hunter, and he wanted in 1904 to go hunting for buffalo, and his staff told him they could only find one buffalo, and they had to capture it and put it on this ranch so he could go hunt it. And he said, "Well, no, I'm not doing that." He said, "I don't want to hunt something that I know I can kill. That's not sport." And this became sort of a big thing for him. And a little later on, he put aside 277 million acres of the United States, and that's our national forest today. And by the way, Congress didn't want to do it. He did it by himself, against congressional wishes. And so that's enough acres to feed 800 million people. So again, population is the issue. That's the population chart. It took 4 billion years to get to the first billion people, and it took 130 years to get to 8 billion, just below 8 billion. And here's all our agriculture and food footprint. So feed and fuel are in purple, and food is in green, food for people. And this is an amazing transformation of the earth that's happened. We think this is good, but some of it isn't, because we've heard our carbon in our oceans, our forests and mangroves have all our natural carbon sinks, and we've disrupted those sinks, so they're not as effective as they used to be. So if you look here, here's another way to look at the current sources and the sinks, and you can see there's a big imbalance, 60% roughly of what we're putting in we have no place to put. So it's being absorbed by the oceans and the atmosphere, and believe me, once a pot of water gets hot, it's hard to cool it down, as you know. So the problem's us, global warming is us, and the solution is us. Just since 2015, the world has added 2 United States from a population point of view, 2 full USA's worth of population in 6 years. That, my friends, is the problem. So why a climate weather forecast now? Well, first, we know about big science. Science has advanced so much, boy, I'll tell you, since I started. Supercomputers, massive data sets with billions of observations, incredible computer models that now run. This thing right here is more powerful than the supercomputer that I did my graduate work on.
Right, exactly.
And attribution science is the latest piece where we can run these models now so fast with great physics and different ones, and we can now look at weather events and tell whether they have been impacted or caused by climate change. This is brand new. This has happened in the last 10 years. And now that we can make that link between climate and weather, we're ready to make a climate weather forecast. So that's why we're here. So some examples, the marine heat waves over the oceans are now 20 times more likely than they were. Major heat waves on the land are now 5 times more probable than they were just 50 years ago. Here's a little chart of all the different things we can use attribution science to help us predict. And you can see some where severe convective storms like, say, a thunderstorm, attribution science is not great at doing that. But extreme cold events, extreme heat waves, droughts, and heavy rainfall, tropical cyclones, we all have skill in doing those things using attribution science. So looking at the effects, here's a summary of from low to high of how understanding the effects of climate change in these various systems. And you can see we're getting better and better at this. And in the next few decades, it'll get really, really good. So our Science Toolkit has really grown over the last few years. And that's why we're ready to make a forecast. The risk of not making one now is much higher than the risk of making one. Is it going to be perfect? No. But I'll just tell you this. Last night we had a little party for our speakers, and a lot of them walked in with umbrellas, and I asked them, well, why did you do that? And they said, well, there's a 70% chance for rain. And I looked at them and I said, okay, I'm telling you, there's a 70% chance for rain. Are you going to bring your umbrella? It's up to you. That's what we're talking about here. So the forecast and the reasons for these forecasts, that's what we'll be talking about. And I just want to say something about myself. This is a tough thing to do because scientists usually focus on what they're good at, one thing at a time. And my background really is from a meteorological point of view. I got into research later in my career, not very late, in my 20s, but I always thought I was going to be a weather forecaster for my whole life, and then I found out I wasn't. And as my career advanced, I have had the opportunity to run the National Center for Atmospheric Research as a director that made the first climate models, and also lead forecaster for the National Weather Service, which predicts the weather. So all of a sudden I found myself with two things that I could do, evidently good enough to be paid, which is sort of surprising, actually. But I think the problem is that we don't have a lot of multidisciplinary scientists, and so connecting things together so that we can bridge it into the future is not as easy as it might sound, because people don't have the career that I had. I was just fortunate that it took me that way, and I was willing to accept it. But here I find myself now, and the CAC in this position to translate science into a way that people can understand it, so we can make decisions not 50 years from now, not planning anymore, but getting up off your you-know-whats and getting going. So the inputs really are all of these things: the trends, the changes of frequency and amplitude of the climate disruptions which we're measuring. We're seeing rainfall and flooding, sea level rise and storm surge, heat waves, forest fires, and droughts. And man, have we had them. So that's a little bit on the global, and now we're going to bring it to local. We know the atmospheric system really is our world, and it's important that we look at climate warming as part of our world, and that's exactly what it is. Here's again a 500,000 year look at global temperatures, and you'll see they were way, way higher before, way, way long ago, 500 years ago. And now we're at this plateau where we've had humankind develop in this very nice transition zone that looks to me like we're about to break out on the upside. So the great warming is already happening. It's already gone up 1.2 degrees centigrade. That's 2.2 Fahrenheit around the world. It doesn't sound like a lot, but here's how the sea levels are, the sea versus the land. You can see how the land is warming up much faster than the ocean, just like you would expect. The Arctic is warming up 2 to 3 times faster than it is here, and the ice is leaving the Arctic, and if it's Antarctica, it will be raising sea levels quite rapidly once it starts. And so this is a very important graph, but the Arctic is a very important place because it amplifies the climate change right here. The IPCC, you've heard about COP26. These are all the forecasts for the future, depending on what we decide we're going to do about carbon. And so you can see it's all clustered between 2030 and 2050, where the signal really starts separating. And that's why the next 30 years is so important. Which track are we going to decide to be on? And you can see in this chart, there's a lot of data here, but if you look at the third column, the temperatures under different scenarios from 1.6 all the way up to the high 2s. So the increasing warming rates are a huge deal. It's not just the temperature rise, but the rate of temperature rise. Since 1990, the rate of temperature rise has doubled. And since 1990, we've started seeing an explosion in extreme weather events. So the rate is just as important as the amount, and that's why it matters. Again, here's another example where you can see it plotted with all the extreme events happening along that curve as the temperatures have warmed. So rapid warming means a big increase in extreme events. We have heat waves like we've never seen before this year in the Pacific Northwest. We know that from attribution science, it's happening 14 times more often than is historically normal. Severe droughts used to happen once a decade, and now they're happening 2 or 3 times a decade. Extreme rainfall is happening with 70% more frequency than it used to. So that's why we had things like New York City this summer. At 2 degrees, the climate disruptions are really going to increase even faster. And we'll see more red tides, more extreme hurricanes, coral reefs really diminishing rapidly at two. Like 99% of all the coral reefs in the world will be dead at 2 degrees. 25% of all U.S. infrastructure will be impacted by flooding at 2 degrees. We're at 1.2 right now. So when we look at what's gone on this summer, in New York City, 30 days before the Hurricane Ida hit, there was a downburst storm there, 1.93 inches, which was a 500-year event in 1 hour in Central Park. 2 weeks later, or 10 days later, on August 21st, we had the remnants of Hurricane Ida hit with 3.7 or 3.515 inches of rain in 1 hour. That was a 1,000-year event. So we had a 500-year event followed by a 1,000-year event. And I remember talking to Elizabeth. She was going to the U.S. Open. This is a true story. I called her on the phone. I said, "What day are you going?" She said, "Thursday." I said, "No, you can't go Thursday." And she said, "Why?" I said, "There's going to be a flood in New York." So she changed her ticket. Then she called me that night, and she was already in town. She says, "Bob, we're in a restaurant. We can't get out. There's water flowing in." And so, what was that, 4 or 5 days in advance, something like that. So anyway, more frequent climate disasters are occurring. And so these are days with billions of dollars worth of disasters. Flooding events and extreme events. We had in Houston, we had 3 500-year floods in 3 years. New York City had a 500-year flood and a 1,000-year flood. Germany had a 500-year flood this summer. Nashville, Tennessee had one. Iowa last summer had an $8 billion thunderstorm. British Columbia is underwater and people have died there this week from 10 inches of rain from what we call an atmospheric tide that hit the West Coast. So in Iowa alone last year, one thunderstorm stayed intact across 770 miles and cost $8 billion of damage. We have some people from Iowa here, don't we? Yeah. Raise your hands. Iowa? Okay. This is British Columbia yesterday. This is the main highway, the Trans-Canada Highway, through British Columbia. They're rescuing people in helicopters. So this is what it looks like from 1950 to now as far as more downpours. So this is the temperature. After COP, which was just ended, the forecast is still for between 2.5 and 3 degrees warming. I'm telling you, we're at 1.2 now. Can we really take that much? I don't know. So that's where I want to, no, it isn't. Here's 2030 on the left, and 2050 is the second pane, and the change in temperature between 2030 and 2050 is the last pane on the right. So these are the different futures that we can have. And I'll let you read these at 1.5, 2, and 3 degrees. I've lost control here. Yeah, it won't advance. Oh, there we go. So the last time that, like you said, the last time it was this warm, water was 20 feet deeper here. This is what Florida looked like then. Yes, and so I have to say that in order to ask a question, you have to come up and speak into a microphone. And we're happy to take questions. Right here. And if you have questions, just line up near the microphone. Yeah, we'll just take a couple. David.
Hi, Bob. So a month ago, you told me you had the answer to the question, why is the Arctic warming that much more than the rest of the Earth? And we didn't have the chance to get you to tell me the answer. So what's the answer? Why is the Arctic warming that much faster than the rest of the planet?
So,
Bob, restate the question.
yes, the Arctic is warming 2 to 3 times faster than everywhere else. Why? Well, part of it is because the albedo of the Arctic is changing. As the albedo is the reflectivity of the Earth. As the Earth warms and the snow recedes in the Arctic, the land is exposed, and land absorbs heat much faster than water does, and ice doesn't absorb much. So think of a white surface, the energy comes in and it bounces off ice and it goes back into the atmosphere and back into space. But when that ice is gone, it penetrates the surface and the surface heats up, and that heats up the air.
So that is also increasing at rate then?
Yes, the Arctic ice is at a record low now. And by 2050, we think there'll be months where the entire Arctic Ocean is